So the aim today then is to use autograph to solve simultaneous equations. And then we're going to look at the exercise as well. Assignment 6 is now out of the way, but a couple of you maybe would look at some of those. And then we can think about assignment 3. So that's the plan for today. And what we're going to do is look at an example of how to solve a simultaneous equation. It's a straightforward example, like the one that we were looking at the session before last. And then we'll look at an example where we've got more than one variable and remind ourselves how we plot that and how we find the constants that are in the formulae so that we can plot it. So the example that we're going to look at is exactly the sort of thing you're going to be asked to do in your assignment. So if we understand that, you'll be able to do the assignment. So first step, if we want to solve something like this, 13.6x minus 21y equals 112.6, 10.9x plus 3.8y equals 109.4. We've looked at that, we reminded ourselves of the algebraic way to do that, which was, if you remember, to try and make either the x's or the y's the same so that we can then eliminate them. Well, that's not easy to do in a situation like this. And you can imagine in an environment where you're doing some engineering, highly unlikely you'll have whole numbers. So when we look at it algebraically, it's usually designed so it's quite easy to solve. But in the real world, that's not how things work. So to try and solve something like this algebraically, we'd have to use substitution. We'd have to rearrange one of these formulae, say the top one, to read x equals something, and then put that into the second formula. So we've only got one unknown, the y. But I think you can see that that wouldn't be straightforward. Better way to do it would be to plot them on autograph. Plot this first function. And we can write it in exactly as it's written there. So if we were to fire up autograph, we could type that top equation in directly using x and y. We'll be able to plot that function. So the only thing to be aware of is that, of course, if the variables are not x and y, then we'd have to assign one x and one the value y, because autograph only recognises x and y. So if that was 13.6a minus 21b, I'd let x equal a and y equal b, so I could plot it on autograph. So 13.6x minus 21y equals 112.6. See if I can remember that. It's highly unlikely. 13.6x. What's the next one? Minus 21y equals 112.6. Okay, and we get the graph. Now, of course, you're familiar with autograph. If it's not there, we need to zoom out. So zoom out, and eventually we should see the line, and there it is. Ah, look at that. I left off the x, didn't I? So that's why we got just a straight line, because x is not in there. Okay. There we go, that's better. Okay, so that's the first function plotted. Now what we're going to do, plot the second one, and we're just looking for where they cross. And that will be the solution. So the second one was 10.9x plus 3.8y. So enter another equation, forgotten already. Was it 10.8x plus 3.8 y equals, is it 109.4, 3.8, 109.4, okay, and there we go. So now we have the facility on autograph to zoom in on that function. So if you were plotting something like this for your assignment, I would suggest that at this point you copy that page, put that in by going to page. It's a reminder, isn't it? Copy pages bitmap there, and then put it into Word. But what we're interested in is zooming in on that solution. So zoom box in on that point. One of the disadvantages of this autograph software, I'm sure you're aware of it, is that it can crash. So if I was doing this, every now and then I would save it somewhere so that if it does crash, I can at least get back to where I was. So now I can zoom in on that point, and end up with values for x and y. Do you remember when we were talking about this, the advantages and disadvantages of using software? That's highlighted here. We can't get an exact value for x and y. It's just a matter of how far we zoom in. I can now estimate x as 9.71 something, 9.712, 713, and y as 0.93. If I wanted a more accurate value, I'd need to zoom in further. The algebraic solution gives me an exact answer, but this is, if all you're interested in is a rough value, then you can use this. Okay? So now I'd print that out, put it in, and estimate what the values are. So I can now look at this and go, right, x equals whatever that is, and y equals whatever that is. So you can use the software to solve simultaneous equations. Just save this into our notes. So there we go. Okay. Right. So, however, what we're often interested in is situations like this. So let's look at this example. There's a function that you might recognize. It's one of the equations of motion that describes the displacement, s for displacement, not s for speed, s for displacement, and how that varies with the initial velocity, the time, the acceleration. Okay? How many variables in that function? 4. S, U, A, and T. Okay? We're interested in how does the displacement vary with the time. So if you think back to when we were talking about these functions and the independent and the dependent variables, how does displacement vary with time? So which is the independent variable? The one that we're going to be controlling. Time. We're changing the time, and we're seeing how that affects the displacement. How does the displacement vary? How does it change if I change time? So time is the independent variable. So the dependent variable is displacement. So what goes on the x-axis? Time. So time is the independent variable and goes on the x-axis. So that's x. And the displacement goes on the y-axis, because that's the one we're interested in. What do we do about u and a? They're constants. Okay, so if I want to plot that, I would put in this formula into autograph. Y equals u. I can leave the letter u in there. X, because my t is going to be x, plus a half a x squared. So I could type that into autograph, and I would get. What sort of line do you think I'm going to get if I do that? Is it what, sorry? Yes, it will be curved, because remember we were looking at the function. We've got an x squared in there, so it's going to be a quadratic. Yeah, when you get that, that parabolic shape. So what we're going to type into autograph, we're going to type in y equals ux plus a half, so, well, 1 over 2, a half, 0.5 is probably the easiest way to enter that, a x squared. Y equals ux plus a half a x squared. So I'm assigning y to the dependent variable, which is displacement, and x to the independent variable. Hit OK, and we get this quadratic. Okay, so this is a curve showing how displacement, so this is displacement, varies with x. So I can zoom out or zoom in on it, shift it around. If I'm only interested in what happens to the graph from this point onwards, which is common because this is time along the x-axis, so we're not really interested in negative times. So in an engineering environment, usually it's this quadrant here that we're interested in. So let's just bring it down here. and zoom in on the x-axis so we can spread out this here and then shift it across. So now we've got the relationship between displacement, which is on the y-axis, and time, which is on the x-axis. So after 2 units of time, possibly seconds, it will have gone a displacement of that. However, we've not worried at the moment about the values for u and a. And that's what we've got to think about first of all. Okay? We've got to find out what u and a are before we can plot this function properly. Autographs plotted something for us, and that's because it by default it sets u and a as 1. So if I go to the constant controller here and look at the values for u and a, the constants are in here. So whatever letter I put in apart from x and y will appear in this constant controller, and I can change the values of them, set by default to 1. So at the moment this function is plotting displacement against time when u and a are 1, which might not be the case. So the first thing we have to do is to find out the values of u and a, and then we can plot the function. So there's 2 parts to this assignment you're going to be doing. The first part is to find the values of u and a, and the second part is to plot the function and then get some sort of value from it. You'll be using a different function, but the principle is the same. So let's go back to here. So in order to plot this, we need values for u and a. To be able to do it, we need some information. So you imagine you were doing this in an engineering environment, and you did an experiment, and this was some sort of object that was moving. It could be a slider moving up and down a machine, or it could be some object, literally a car or something. So what you do is you get some values, you do an experiment. We let this thing move, and we notice that after 13.68 seconds, the displacement, how far has it gone? 918.344 meters. So we've measured it pretty accurately to the nearest millimeter. And then it's continuing to move, so it's one experiment. We note after 68.4 seconds that it's now at a distance of 22,950.39 meters. That allows us to set up 2 equations to find u and a. We've got 2 unknowns, u and a, so we need 2 equations, 2 scenarios, 2 sets of information to be able to find what they are. So what do we plot? Here's the function. So what we do is we know s. It's 918.344 equals. We don't know u, so that's just left as u. We know that the time, though, is 13.68. So it's u times 13.68, or 13.68 u, to put the letter after the number. Okay? Equals, plus a half a, so 0.5 times a times t squared. Well, we know t, so 0.5 times t squared, which is 13.68 squared. So that's a little calculation I've got to do, and then that's times by a. So that is the first equation. We've used the information from the experiment, the first set of information, to set up an equation by replacing s and t with the values that we know. What about the second equation? Just write down what the second equation would look like. So second equation will be this. Now we want to try and solve it. Well, we're not going to attempt to do this algebraically. What we're going to do? Plot it on autograph, okay? Work out the numbers as far as you go. Autograph is not going to like you putting this in, 0.5 times 13.68 squared. So work out what that is, and work out what that is. So if someone can do that for me. Pardon? Yeah. Oh, yes, thank you. Yeah. Okay, so we now have two simultaneous equations that we can plot and autograph. One more thing to do before we can plot them. What's that? Yeah, we've got to assign x and y to u and a because autograph doesn't recognize u and a as variables. So let's let u equal x and a equal y. It doesn't matter which we call which, but let's do it that way around. And now we can plot those onto autograph. So plot them. So here are the two equations down here entered. Obviously we can't see them because we're looking in the thousands here, so we need to zoom out, I would guess, quite a lot to be able to see them. So let's zoom out. Here they are. Now to be able to get it, we need to use these buttons here to change the axes around. Everything is happening within quite a small band in the y-axis here, so we could do with zooming in on the y-axis to open out these values. So if you want to open out the line so they're not right close to each other, that's what we can do. So now we can zoom in on it. Zoom box in on this point here. Now we can start to see that it's all happening around this point here. So again, we could do with zooming in maybe on the y-axis to separate out these points. And then zoom in again. So it's using the buttons on autograph to zoom in on the values. Again, we could probably zoom in on the y-axis a bit. And then, and so we can now, so we've hit a problem where it would have been a good idea to save this, unfortunately, see. So now it's gone, so I've no idea where it's gone. So try zooming out. Oh, here we go. So yeah, but that's a good opportunity. Maybe if I'd have saved it, then, you know, I've noticed this happened before, so you have to be a bit careful. So let's zoom in once more. It's done it again. Doesn't like that, obviously. Okay, so let's leave it at that point. Now we can come up with some values for x and y. So if we arrow down and arrow across, we can come up with values for x and y. So it looks as though x is around about 0.031. If that's 0.031 and that's 0.0312, so that's 0.311. So it's about 0.0314, something like that. No, 0.4. Because that's 0.0311, this point here. So that must be 0.03104 or 05. And this one, about 9.8 something. So about 9.81. It's near enough to 9.81. So let's call that 9.81. I probably zoomed in a bit far. 9.81 and 0.03 will probably do us for values for x and y. So let's put this in our notes. Yeah, but it's not far below it. If you look at the scale, it's all very close to 9.81. Yeah. Say that again. So what have we got? We've got the fact that we've got a function, here it is, two situations. We know that when the time is one value, the displacement is 918 point something, and so on. So we've got two situations. We plug these into here to form two equations, 1 and 2. We've assigned x to one and y to the other, and then we plotted it on autographs. So now u is on the x-axis, so this is our value for u. So u equals 0.03, and the other a is 9.81. And you might recognize that number a is the acceleration due to gravity in this case. So it looks like the object is falling due to gravity because we've come up with a value of 9.81. Right, but we've come up with that. So we can now go back, and we've got s equals ut plus a half at squared, back to our original function. And now we know that u equals 0.03 because we've arrived at that using autograph, and we know that a equals 9.81. So now we're ready to go to the next part of the problem, which is to find how does the displacement, remember, vary with time. Now we can do it because we've got values for the constants u and a. So we can plot s equals u, which is 0.03, t plus 0.5 times 9.81 t squared. So that's the function we're going to plot now that we know what u and a are. For autograph, there's two things we need to do now. One is to work out what 0.5 times 9.81 is, and then the other thing is to assign y and x to s and t so we can plot them. Remember, t is the independent variable, so that's going to go on the x-axis, so t is going to be replaced with x. Y is going to be the displacement on the y-axis, the one we plotted in other words. Now we know values. So what's 0.5 times 9.81, someone? What is it? Sorry, 0.4 something or other? 0.4 point, yeah. 4.905 x squared. So that's what I'm going to plot on autograph. So if we go back to the function we plotted in the first place on autograph, which was, we close this one, this function, we played around with it with u and a set as 1, remember. So you might find you want to plot just s equals or y equals u x plus a half, as we've done here. But what we're going to do now is actually change this formula to the one we want to put in. So y equals u, which is 0.03, x plus 4.905, was it? X squared. So now we plot that and we get this function. Okay, so that's the one we're interested in. We're now plotting displacement against time for this particular scenario where u equals 0.03 and a equals 9.81. So again, if we're interested in this particular quadrant, we might want to zoom in on the x-axis so we can stretch out this curve. And now we can answer questions like, how far is this particular object that we're interested in going to go after 1 second? So we did an experiment, but now we have a way of predicting where this thing is going to be. So after 1 second, we can go up and across and say it looks like it's going to be around about 5 units of measurement, whatever we're measuring in. How long does it take this object to go a distance of 10 units of measurement across and down, and we can estimate what it is. and then to get the answer accurately, I can zoom in. So if I'm interested in this particular point, I'd zoom in on that part of the curve. Okay? So a quick recap. Let me put this into autograph. So I'll just pause for a sec. So here's our function. It's got 4 variables in it. In this particular case, we're interested in how displacement varies with time. So the first job is to decide which is the independent, which is the dependent variables, x and y. And then we've got to find out the constants, u and a. And that involves setting up some simultaneous equations. 2 unknowns to find, 2 simultaneous equations. 3 unknowns to find, we'd have to have a situation where we had 3 equations we could set up, and so on. So we've got 2 unknowns, so we set up 2 simultaneous equations. We need 2 sets of information. There they are. So we rewrite the function with those values in, simplify it as much as we can, so we can plot it onto autograph. Then we assign x and y arbitrarily to our constants, u and a, plot it on autograph, and then we can zoom in and find the values for u and a. Once we've got u and a, we put those values back into the original function so that we can then plot the original variables. So now we've got the dependent variable, which is the displacement, plotted against the independent variable, which is the time, with the constants now put in, simplified where possible to give us that. And then we plot it on autograph, and there's our final thing. So that's the sort of thing I want to see in your assignment. I want to see the graphs plotted and then put into your assignment so you can paste them into Word, as well as how you calculated the constants. Okay? Questions?